So today we're going to go over a few things, and quite a simple, like, I don't know, we have 45 minutes. We can stretch it a little bit, but you know, we're going to go through what's diffuse, why, and what's the open source version of it. Why did we decide to open source? We're going to install it quickly. I'm going to screen share. I'm going to show you a few commands. You know, if you have any question at any point in time, please drop them in the chat. Even if they're not answered in this session, like if you have large, big question, ask them, because that will inform maybe the next videos we're going to build. And, you know, I'm going to make sure we figure out a way for you guys to have these things answered. Okay. So it'll give you some anchors there as we go through things like flag, you know, questions, whatever. Okay. So, and then I'm going to boot a chain in there. And I'm going to answer the questions. Does that work for you guys? Raise your hand, say yes, whatever. Oh, good. You're fast. So you have the button on that raise hand. Okay, so let's do that. I'm going to share my screen right away, and I'm going to show you. Oh, there's a lot of windows here. Just a second, okay? Before so I have Emacs open, so that's good. I'm going to share my screen here. Okay, and I'm going to show you this terminal there. And in there, we're going to boot. In here, I have a project. It's called Demo Project. And I went and I installed, actually, I installed from source, right? If you check out the project here from the git config, I installed it from, sorry, it comes from dfuse.io here. That's the repository. So you can clone that. And then from in there, if you have the Go tool set, you can install it this way, dfuseeos. Boom, I already built it. Or another option is for you guys to go to the dfuse.io repository, get one of the latest releases. This is still beta. This is, you know, the repackaging, a lot of change going on. You can get the Linux version and the macOS version. This is a repackaging of what we initially had. You know, split in different chunks. So the exercise for us while we open source is to make it and package it into one binary, which is nowadays dfuseeos. So I'm going to go in proj and then demo. And what I did here was dfuseeo init. I answer the question yes. And it merely gives us, you know, a few configurations like a config.ini, which is something known to most of you guys, right? With the default keys here, the standard development key. And it has a mindreader. If you have any questions on the different subsystems, I can answer, but there's a few of them, so I don't want to take so much time on each of them in this webinar. And the special sauce here is the DeepMind enabled config for the mindreader. That's where the diffuse, let's say, magic, they do hide a chunk of the screen. You mean this side? This side here? Okay, I can't move it. I'm on the Linux version. I know they didn't give as much care to the Linux version as they had for the other ones. So, okay, so if someone is interested in the Docker setup. And over here, we have the demo. And what we'll do first, I usually start by purging. It merely deletes the diffuse data directory here. And after that, it's clean. So we can, so the only remaining files are you know, protocol features directory, a config, and a Genesis JSON, and these things. Okay, now, next step, diffuse eosc start. Now what that will do, it's actually going to run in a single process all of these sort of, we call them apps, all these small apps. On our infrastructure, they're often split in different pods, different containers, or you know, you can imagine different machines, whatever. But here they're all booted together and they're all interconnected. If we look at dfuseeos starts flags here, you'll notice that there's a lot of addressing going on. This one is the HTTP address. That's a target address. Let's say, you know, the dgraphql. That's one of the services. It listens on this address and this one. And another component that needs dgraphql is also pre-configured. So there's a series, maybe, I don't know, 20 ports. And all the thing connects together. It means that when you run all these programs on your machine, you can very easily go to another tab, diffuse start, and then select only, for example, API proxy. And that will run only the API proxy, yet configured to connect to your local host on the next, well, so now it's already listening on the previous tab. But you know, if you hadn't run it on the first tab, it would then connect, and you can start decoupling and splitting apart in a very, very simple way. Start with one core and split it in chunks and then start scaling the different systems. Because what I wanted to say is that we've decided to open source. I'm going to stop my screen here. We decided to open source this, and here, I don't know if that was done already, but okay, we decided to open source because we wanted to empower people more. We felt like having a proprietary product was not as empowering for the community. I remember with starting with Bitcoin, right? And I remember feeling like, wow, that's in 2013. The first emotion I remember was that, look, I get to handle that myself now. I am empowered to program money. That was amazing. And we felt that we couldn't give that same amazement to people by having just the APIs available. So we decided to open source. It's also really part of the ethos in the ecosystem. And we're big open source fans. And so we started doing that. And actually, we think it's a very good move. And what we decided to open source is everything. All the things that you have in the current repositories are the same thing that we're running for the hosted version, for the grand scaling version. We've worked a lot, to scale to mainnet size deployments. You have there the third or fourth iteration of most of the components, the search engine, the B-stream machinery. So it's a very refined product that is out there. And the only few bits that we didn't open source, which doesn't make sense to open source, is our authentication layer, which is now abstracted. There's a very clean separation for when you want to hook in authentication middlewares, and if you want to hook in billing and metering and things like that. All the stack is Prometheus instrumented, so you can just hook Prometheus, put a Grafana, and it's fully monitorable. We do that this way, yeah, so the only thing we kept is because it's tied to our portal, the way our users are, authenticated and are set up. But otherwise, the whole thing is out there, okay? So there's no difference between this single binary than what runs on a super high scale network. Hope that is clear. So the open source is sort of full on, and then let me just see the next points there we want to make sure we cover. Okay, so I'm gonna boot it. Have I booted it? Yeah, I did. Okay, let's share my screen again. So the thing is booted. If I open here immediately when I boot, let's start it again, okay, just to see how fast it is. So I'm gonna purge it. Okay, and then I'm gonna start it. And when I do that, I can go directly to the dashboard on port 8081. And that's a specialized dashboard we built. This gives the status for all the products, for all the apps. And very soon after, they're all gonna start feeding blocks, start setting up, and see they'll all be ready pretty fast. Search Live is going to do indexing. Okay, I see what you guys meant, right? And now it's all set up, boom, everything is green. This is awesome. It's not always been the case, but today works pretty well. And if we go in here and we have a localhost 8080, we have eosq and started producing blocks. And then let's boot something. See, this is live, and I can also get to the dashboard, go to GraphiQL. For those who don't know, that's the sort of GraphQL interface, and we can go in there and say receiver EOSIO. Let's say a limit of 1,000, and then let's stream that. So we're doing a query. It's a live query. I'm at block 1020. This is live. It goes alongside. I can get all the actions, specialized, and this is fully aware of forks. It's a very powerful system. I might get into that in some other videos, but if you have questions, I can answer. But so that's it. So now let's boot something in there, meaning let's inject a boot sequence. And some of you guys remember just a few days ago the anniversary of the second year of EOSIO's boot. And today we're going to do a very similar thing. We're going to boot a chain using the same tools we used to boot a certain chain that didn't become mainnet, the 579A chain. And EOS BIOS became folded in the eosc tool. And let me show you just the boot sec. It's a very complementary tool here where we list all the contracts and the keys we're going to use in there. And it's declarative way to boot the chain where we set code and the reference is the BIOS in there. We can have a hash to be sure that we're not we're booting the right thing. And if you look at the eosc repository, actually in the boot sequence, you'll see that there's a launch clone in there, and the boot sequence is the original boot sequence. So this is still the files that we used originally. This is the hash of those files, and this is exactly what we used to boot the chain. So today we're going to use a simpler one. There's no snapshot. We just want to get things running, put a few contracts in. So we have token, msig, and a few things like that. And it's going to be very simple. We're going to do boot like that. And the default parameters, so it's going to use a small eosc vault that I have here. Password, very simple, and it contains that famous key that is sort of the developer key. And if I do eosc boot like that, then it's going to inject in the chain all these operations that is declared. It's then going to get all blocks and validate that all of the actions were properly inserted. And if we go back to eosq so localhost 8080, and we see, so if we go, we see the on blocks, they go pretty fast. Maybe down there we have something. We can go and query negative action on block. That will tell the search engine to give us everything that is not an action on block. And here, and we can see these are the things that were arriving block 357, and the things they did, new account, whatever, and then we updated permission at the end. So we have a booted chain here, and we could do something similar here, receiver, I don't know, like action on block, and go from the start. And then we have these, right? And we're still listening if there's anything coming through. So that's how we can very easily kickstart the chain. Now, the 8080 port also dubs as the API proxy. Where's that listed here? There's a little thing, API proxy. This one actually blends. It's sort of a small Nginx, and will send to the right services the different endpoints that you find in the configuration. For example, the state, this one, the block goes to a certain service, the state goes to a different service, and the push transaction, whatever, these things go to different service. And nodeos is also sent directly to the node, and the WebSocket is a different service, and GraphiQL also is a different service, but they're all exposed through that port 8080. So it means that you can now go on your command line there, and let's say this here. So we booted the chain with this block. What's in there? 1015. Can we get something? This is the get block ID by time. 1015 means probably 14. And will that work here? So here we got the block at that particular time. We're at the comparator, so that's hitting one of the services, but they're all blended behind port 8080, right? And same way, the dashboard here, will connect through that same port and do the queries, which you could also do on the command line. So I guess that's a quick introduction. Now I might want to say that I didn't install nodeos here, but you want to install nodeos. I'm going to run through that, and I'm going to explain maybe the small differences. So when you go install diffuse for EOSIO, you actually need a node there. And the node you can use today is our fork of the node, because it includes, so we've released that we call it the DM version, DeepMind enabled. Okay, this is temporary because the changes that we modified in this nodeos have been merged in nodeos' trunk. So the next release, maybe not 206, which was released yesterday, but the release of the next milestone is in the develop branch, so 2.1 perhaps, I don't know the scheme over there, but for release from block 1, that will include the -- DeepMind, and in that case, you will just need a stock nodeos to be able to run with dfuseeos. So use the standard method for deployment. Right now, you will want to use either Ubuntu 16, 18, or we have a version also somewhere. Don't we have a version for Mac or something? Anyway, the guys have that. So that goes on for the installation, which is pretty simple. And in there, that's the repository. You have all the components pretty well separated that were brought together in that single binary experience where we boot, a new chain, which is an awesome, I think, developer experience. Want to start developing, but also if you want to use the search engine, FluxDB, and which is the state database at any block height. You know, you could run these things separately in tandem in a single binary or all split. Does that work? Now, I would like to take on some questions if there are things that can, you know, just direct a little bit.
I think one thing, Alex, that might help is Ross had asked, and Jack as well, if you can use your whiteboard to just give a quick high-level overview of how the components work together.
Okay, I know that's a sought-after question, right? So let me come back. I'm going to share the screen here. Okay, so you Josh, you bring in the questions. I'll close the window for the Q&A here. So if we're looking at these components here, ABI codec. Okay, I'm going to give a quick run through because you asked. ABI codec is a small service.
I want to swap your screen so you're bigger.
Yes, so everyone can adjust that normally. If they take the webinar and then they scroll it, you can take the little bar in the middle of your screen and scroll it on the side because I wanted to show the list here. No? Okay, you take a snapshot of that.
Perfect.
Okay, so ABI codec is a small service. Its role is strictly to do ABI encoding. ABI codec is aware of all of the ABIs at every block height, so you can say, decode this at that block height, is going to do it for you. It's a small service. Its only purpose is that. You can scale it separately. And then we have API proxy. API proxy is a thing mostly for development that will route requests to the different services, okay, that are user-facing. ABI codec is not directly user-facing. It's the gRPC service that is exposed. I think we have an ABI to JSON endpoint, and that might transform requests and send them there, but this is not directly exposed to users. And then we have blockmeta. Blockmeta is sort of the spinal cord, very central. Blockmeta is aware of one thing, the series of blocks, their irreversible status, the state of the network, the state of, you know, the systems. So it knows about the, you know, the state of the chain, but in a very thin way, about blocks. So you can always, so all the systems that, for example, boot, they can turn around and ask blockmeta, what's the highest block currently? Am I in catch-up mode? So yeah, it's this sort of a central piece that is only aware of a few things, but it knows the timing, so it can answer questions about, you know, the time before and after a certain block. That's what it does. It has a backing store, the same backing store as the other one, which is trxdb. Let me see the next one. So dashboard is also a specific thing for developers. So I'm thinking users here. Do you see that? Maybe the screen is a little tricky, huh? So dashboard specific for dfuseeos. I mean, the single binary and laptop experience, we don't run that in production. It's mostly for, you know, for you discovering what's the state of the things without digging into command lines. Then dgraphql is a user-facing product. API proxy will send it. This serves the GraphQL interface. And this one will communicate with all the backends to satisfy their needs. Notably, you know, the search backend is not directly exposed. dgraphql in its streaming search will talk to the search through gRPC. So serves only subscription and queries with the GraphQL, let's say verbiage or vocabulary or interface. Then we have eosq, which is also an isolated thing. This will merely communicate with all the other components through the same APIs that are exposed to users. So it's a pretty standalone application. I have to say there's a few endpoints that eosq uses that were never documented, and we don't want to, so we'll eventually move these APIs to dgraphql. So there's a little bit of that I don't want you to look, right? Okay. Then there's eosws. eosws is another front-facing component. eosws is the first product we built, really. It was about doing WebSocket. It's the first streaming. That's where you get action trace with our own WebSocket protocol. If you look at our documentation, you'll see the WebSocket interface there that we built. Get action traces, get streaming deltas, and a few things with the listeners and whatnot. Today, I think the search is more reliable, more robust with this cursor than the WebSocket is for getting transaction. But there's a few features that are still in there. eosws also is ran here It also contains the push guarantee endpoint. At the first, we added there a few features before splitting those in different microservices. So eosws contains also the push transaction. So when you send /v1/chain/push transaction, and you have that little header that says, wait until it's in block before I get anything back. Well, then it's going to do the work. It's going to install there, it's going to send the transaction, wait for blocks to come back, and then fetch the transaction traces and give you those, so that you get that guarantee and that, sort of atomic round trip and your guarantee the block is produced already with your transaction in it. So eosws has those two things. FluxDB is a database, right? FluxDB is it's actually a great innovation. It's a specialized database to snapshot all of the tables of all of the contracts of all the chain at every block. And it has a specialized indexing mechanism so that you can query at any block height. It's going to start from snapshot, replay just small segments, but give you pretty fast, consistent, coherent snapshots of the state anywhere. This is particularly useful because oftentimes when you query directly one node, when you query a single node, you query by paging 1,000 by 1,000, but the block time is so fast that you'll query 1,000, then you get a lower bound of 1,000, but then it's moved, right? Because a new block came in, maybe there's a transfer that went from here to there, so it's very difficult to have a consistent view of a table if you query the node directly. And you cannot expect the node to hold the state for every point in time. It would be just very fat and big. So, FluxDB is backed by a very simple key value store, and the keys and values are set up in such a way to make this possible. And we've tried with many other stores, and we ended up rolling that specialized solution for that particular problem, which works very well. So that's FluxDB. And in FluxDB, we have an ingester and a server that you can split apart. Right now in the service there, they're both run with ingester plus server, but you can have many, many servers that serve requests and one ingester that loads that in your key value store. So FluxDB, two little components, one app in this little thing. There's a few flags that distinguish the two modes of operation. In this setup, there's both ingester and server. And this is exposed. So today, FluxDB is still not gRPC based. It is REST. So it's actually a pass-through through eosws directly to FluxDB. And it serves back JSON in a streaming fashion. Our goal is to bring that to gRPC and refresh a little bit the behavior, because there are many things we can build on using FluxDB with this particular sort of snapshot and back and history way of doing things. And FluxDB is also aware of forks. If you connect to it, it can stream you, and navigate forks, reorganization, and undo things. So it's pretty interesting. It knows about the reorganization. And we have a video about bstream, which is the libraries that we use to be able to, in every component there, understand the tip of the chain and the risks and eventually consistency dynamics of the chain. Then I'm looking at the merger relayer. Okay, let me quickly draw that. I have a video about that. So that's an important bit. This is part of the high availability setup. This is mindreader. Mindreader contains nodeos. Nodeos is in there. Yes, this is nodeos. It's an egg. Yeah, it looks like I don't know, Pokemon. And then you can have many of these, and they'll all be funneled through relayers, but we also want to have them be highly available. So this is connected to the peer-to-peer network. The blocks, information, and traces are produced, and then you have the relayer that will consume it from one and from the second. So it's highly available. If this one drops, it doesn't matter because you have another one at the same time. So this is relayer here. And if this one dies, everyone can connect there. It's not missing a thing. So you have a highly available setup. This one does deduplication because it also is aware. It uses those fork DB implementation. It's a re-implementation of the fork DB from within the node externally, so you can always have an understanding of the current, longest chain. And then separately from that, there's the merger, which takes all the things produced by these ones and fuses them together to get a sort of a backup that we can reuse later on. The merger produces those 100 block files. Those 100 block files are akin to this ship state history plugin, except they're easily, parallelizable. One thing we do is we process chunks of the chain, provided we have continuity in those 100 block files, we have full history. So it's a lot more flexible than I think than what we have with ship. And the mindreader implementation there is so tightly bound that when it produces those blocks, you never miss a block in there, like and empty a buffer or have a discrepancy, and you don't need to feed it anything in there. It's extracted as fast as possible. The merger builds the 100 block files, and the relayers relay the real-time data. So when you want to have something that, I don't know, boots or needs to process 1 million blocks, let's say your database is out of sync, and we have the fluxdb ingester. An ingester turns around to its database, I'm missing 1 million blocks. So it's going to fetch files from there and connect to the live system. And then it's going to start streaming linearly from this and from that and hand over. That's the joining source that's detailed in the vStream video. Take a look at that. And it's going to stream extremely fast. The 1 million missing blocks go linearly and feed out, FluxDB. All the systems are aware of that setup, can connect to that, can consume those files, and they'll this way they know they never miss a beat. And also the merge files will always contain all perceived forks. So that's an very important difference, I think, is that if we ever send you a fork, we're always able to get you out of it because the merge blocks will contain, all of them. And if we had 75 mind readers and we perceived 75 small forks, not much chance, but 1 or 2, it happens. We will have them all in the end. And if you come back with a cursor saying, look, I was dropped on this fork. Can you get me out of it? What do I need to undo to get back to the canonical chain? We'll have it in the merge blocks, right? So we can get you out of there. Okay, this is fast. The mindreader and node manager so the 2 components, mindreader and node manager, these are managed nodeos instances. Node manager is used in the local desktop setup or laptop setup, or desktop if you want. Is used to run a nodeos that is going to be producer nodes. If you're launching a small, like my network here, has 2 nodeos running underneath. One that is producer, one doing the mind reading. Mind reading is really read-only. You don't want to use that for doing all sorts of things because you want to, the full strain must be there to exfiltrate data. It adds a little load. So on a network, if the network is very saturated, you don't want that node to be doing other things, just taking the data out as fast as possible. And that's pretty fast today. And so node manager, just mind you, node manager is backed by a piece of software called manageos. And manageos is what we use as block producers to run our nodes. So it's a fully instrumented program that has an API where you can shut down the node, do backups, do recoveries with 3 methods, like using cloud providers, using Pitrios, using snapshot, state snapshot, and all these things. So heavily instrumented, and you can control the node. You can watch the peers disconnect and reconnect if they're not properly connected. Does that make sense? Is everyone still there?
Yeah, it looks like we got everyone still there.
Okay, cool.
I think if you want to go on to the next one, Alex.
Sure.
Sorry, I'm asking about the apps. If you have to recommend which apps can be grouped together and possibly shared among different chains, just from an architectural standpoint for
group together what? To group together what? Apps?
So if he's building a big diffuse farm, as so to speak, which apps would you recommend could be grouped together?
Let me finish. There's 2, 3, 4 more apps, and then I'm going to give you an idea of how they group, okay? There's one other app, which is trxdb-loader. trxdb-loader is another database. It's still backed by the same key value stores, but its goal is to store blocks, transaction traces, and block times. So very simple to the point keys, and the values are the block headers, or the values are the traces for a given transaction, or the body of the transaction without its trace when it's not executed yet or whatever. And so very simple trxdb. And trxdb-loader, what does it do? It connects to those mind readers and block files. It injects them in the key value store so that eventually, when you have the GraphQL interface that needs to have access to the trace of a given transaction because a user requests it, turns around to that key store, pulls it out extremely fast. because the way kvstores are laid out, it's very optimal to do exactly that, right? So, and so we have 3 backends for kvstore. We have Badger, local, like RocksDB. We have tikv, which I encourage you to take a look. It's a distributed key value store, very simple. It's the backing store for tidb, which is a MySQL drop-in replacement, but that uses methods inspired from Google Spanner and HBase and whatnot. A tikv is a small, written Rust, small, just key value store that you can horizontally scale, run on-prem, run everywhere. It's incubated by the CNCF, very interesting project. So we support that. And we support also Bigtable merely as a key value store, right? We can use that also fully managed, scales horizontally. So it's been very solid for us. And then it could be pretty easy. It's like 500 lines in interface if you want to have another key value store. So tidb is based on that. Now, there's all the search machinery. I think that's important. We touched a little bit on the search because I haven't made videos yet, but I will. And it's one of the complex systems. Let me show you that a little bit. So we have the source of blocks. Imagine there's those 100 block files and also the live source, whatever here. And it sort of, as a joining source, goes into the search indexer. And search indexer produces small indexes. Okay, just to give you an overview of the search engine, it is based on the Blevy search indexing system. Blevy is similar to Lucene or Solr. It is the indexing engines that underpin whatever Elasticsearch or other systems. This one is the one that underpins Couchbase. And yeah, exactly. So if you go, they're the maintainers of that thing. We've contributed to that thing. We've had people improve the size of these indexes. So it's a very robust indexing engine. It's a full text search engine. It supports geo containment and bounding box things. We don't expose that today. We always wanted to keep a very simple language for people. The truth is the search system we have there could do a lot more than what it does today in terms of sort of queries and composition and ors and ands. We expose a very thin layer because we always wanted to make sure that we could implement it differently if we chose to abstract that one away. But anyway, that's still what's used there. So search indexer will produce small indexes and let's say 5,000 blocks or 500 blocks. And when this index is ready, it's going to put that in an object store, let's say S3 or whatever. We support 4 index store, Azure, S3, Google Storage, local file systems. And again, that's an abstraction that's called dstore. Can easily add another one, 200 lines if you want to, just a few methods, write, get, object, whatever, if you have other other object stores. But use that heavily because then the archive, and there's the live, and then there's the fork resolver. You see that? Just 3 bubbles there. So the search archive will periodically look into there, and then it's going to load the index and add it to a bunch of indexes. So the search archive literally has, right now on mainnet, I think 15,000 indexes. And when a query comes in, it goes and it sprays those in parallel, like we have an optimal path, right? It starts with the beginning, if there's no result, and it accelerates to go over the indexes, but it also means it's very flexible. So we can have these things be indexed in parallel. So for mainnet size, we can index the chain in 45 minutes, just put a lot of CPU cores, but 45 minutes and full of mainnet is re-indexed, and then you just need to boot that thing, download perhaps a few terabytes of data, but then it just boots and it's ready to serve. So that's an interesting feature. All these things are sort of managed or register in a small etcd cluster, which has a few nodes, whatever, 3 for reliability there. You see that? So they all register in there and they announce their state, whether I'm, what's the block range I can offer. The live will say, I am live, I get truncated from time to time. You can have a very complex and dynamic configuration of how many of those ones you want, and what's the block range they're each going to serve. You want 5 of these, and then they overlap or not, and one would be truncatable, so it would just have a moving window. And in front of that, you have what we call the search router. The router understands everyone that's registered there. It's going to route requests here and there, and the live router here is the component that will do the real-time search. So that's very fun and specific. This one is fully aware of the state of the network in terms of reorganization and forks and all of that. And it will have not 5,000 block indexes. It will have 1 block indexes. And they're just going to be in memory, and they're able to query, you know, a given chain path and undo the request, undo so if there's a reorganization, it'll apply the search for the user that's waiting there on the WebSocket stream. It's going to reverse search and then revert and search forward. Each time there's a new block coming, there's a new index, everyone queries the new index, and then out goes the results. So, you know, it's still the full power of the Bloody search engine, but now, you know, very laser focused and applied, and you can scale that live search independently, provided it's, you know, connected to the initial mindreader and has live blocks flowing. Each time they're all going to index and then apply all the users that are waiting, that are sort of pending or listening, apply the searches and send out the requests, send out the responses that match. Maybe nothing matches, but right. So archive. Oh, there's the last bit. This is, I think this is, it goes to the extreme, right? Because archives only go towards, only store irreversible stuff. The live will most of the time only store the reversible stuff. And they're still tailing together because they know who is there. When there's a certain threshold of coverage between, then the live will truncate and it's going to still move. So it ensures, everyone ensures that there's no hole, so that when you search the chain, you know, you've got coverage for the whole segment. And the last bit is the fork resolver. The fork resolver is for when you get a cursor and you were left on the live search and we gave you a result, but you come back a week later, and a week later, you would like to know that, okay, this has been undone. You want to get to the longest chain. Well, this little thing has been undone. The fact is, Search Archive only has irreversible stuff. So we built a special service. It's not used very much, but it just shows the robustness of the solution. You can go, and when we discover that you're bringing us a cursor that is forked, but in the past, we'll see if that block was irreversible. If it's not, then we go and ask the fork resolver to fetch that little segment that needs to be undone, to index on the fly those blocks, to replay it backwards. See that? Replay them backward until you hit the trunk of the main chain, and then the router will shift off to the archive because it now knows it is on the irreversible chain path, and then it's going to hand off to the live. So I think it's a very robust and complete solution to make sure, I don't have that t-shirt today, but you never miss a beat, right? We've gone to a lot of extents to make sure that the experience is absolutely flawless. You'll never get in a hole, you'll never get stuck, even though these things are on parcometers and they connect to the internet once a week, right? They might have a false thing, but it always be able to come back to what happened to that parcometer if they update config or whatever. I don't know, you know, IoT things, they won't always be connected. So being reliable and supporting disconnection, I think is very important. That's why we built these things. Okay, so it's 43. I'd like to address more questions than just going into some subsystems. I appreciate, and I'll go and I'll build videos going into these things more in depth and more specific so you can and tackle them. Question?
Just a quick question from Max. So is diffuse EOSIO meant for production environment or launching a new chain, for example, or is it only meant for local testing right now?
Okay, good question. As I said at the beginning, what you have in diffuse EOS, the binary, is ready to go to infinite scales, right? It is not, so if you run it with the default configuration, it'll store everything on your local disk. That doesn't work very well because you'll need to have a disk, I don't know, of 10 terabytes this way and then another 7 terabytes that way. And you know, you don't want your system to be burdened with that. And then what you do, you add another disk and then you change directory and moving that. It doesn't make sense to run that on your laptop because it uses the default backend is Badger, similar to TRXdb or LevelDB, runs on disk. If you want to go to larger scale, you'll need to set up a kvstore that is networked, that is distributed, that, you know, that can scale horizontally, because now each of these pieces are more at risk than on your laptop, right? And if they get a lot of hits, then you want to augment, you know, the scale, and you can't do that with a Badger instance. So if you loaded the whole of mainnet in a Badger instance, Well, I mean, you're stuck to one process. Badger is not a shared database. You can't have two processes reading or writing to the Badger thing. So it works for a laptop, but you need to have a little bit more configuration when you're doing that on a larger network. That being said, everything that you need to get to large network is there, because you do have support for large scale key value stores. We can add these things very easily if it doesn't satisfy your needs. If Bigtable TIKV is not sufficient for you, or you'd like to put that in a MySQL just because you have, I don't know, free MySQL access and you want to hack it to be a key value store, that could be done, right? Because the primitives that we require is just a simple key value scan of keys that are assumed to be lexicographically ordered and a prefix search. Those very simple primitives, and you can bake that on top of anything else. But what we have observed is that when we're using those real KV stores, we can actually massively parallelize ingestion. Again, we're able to ingest, like replay large networks like mainnet, and it will inject like millions of writes per second, millions. And what we do is we boost the clusters, and then we scale them down after the writing, and it all sort of repackages the data. But we're able to do that in an hour or two. Right? It's very fast because it's simple. If you use MySQL to do transaction to add rows, it's going to be very, very slow. So we've taken those decisions early on to get the simplest storage we can, because we get the most performance. And everything that you see in dfuseeos was always designed for massive parallelized operation. So I think in terms of, similar to the ship files, it's very difficult to parallelize these things. You need to have those files need to be cut well. Today, we could produce the 100 block files by having snapshots running for a segment. They each contribute a segment of the 100 block files. Then once that's done, we can start the second layer doing the search indexing. And that also can be fully done in parallel. So then when we boot the machine, they're done. FluxDB is sharded in a different way. So we take the whole history, we shard it in small chunks of tables, each with their set of tables, and then they're injected in parallel because they need to be done linearly, because the way FluxDB works, you want to have them literally, but they're all done in some smaller shards. So everything was always designed to be extremely fast in reprocessing. That's what gives us agility to adapt and create new products and build on top of that. But that's also a benefit you get when you run dfuseeos, is that you have an infrastructure that will be able to survive hiccups, replay fast. And I'll talk about in the search videos a few other things that, to get back on your feet with a search engine, those large 5,000 blocks incurred too much delay. So we have smaller shards to allow you to do a parallel replay near to real time to get, when you have an issue with your node, whatever it boots, a machine crashes, whatever, you can be very fast at coming back. Does that answer the question? I guess I drifted a little bit, huh? But
well, thank you for that. I just want to be conscious of the time. It's a little bit past 10:45. What we'd like to do is I'm going to drop a link for you and Alex. What we'll do is we'll stick around for a few minutes to answer a couple more of the questions that are in the Q&A already. There's also, don't forget, we have our repo. I'm going to drop the link for you again right here for everyone. If you guys can go and show us some love, start the repo for us. And Alex is going to move on. There's one question from Daniel Prado. Is there an official support for Kubernetes to host diffuse?
So maybe I can address the question out there by Steve about Docker. We run everything containerized. And we run everything in Kubernetes. So it is obvious to us that this is, we designed it to be sort of Kubernetes native. So it will run in that context. We have one of the things we did in open source is all the knowledge of operation. So our guys, they operate that. That's a lot of the knowledge, and we don't have that much in code that much. We do have a few tools to help us out, but I don't know if that answers the question. Kubernetes is very welcome and supported in what we do. Docker is the first way we deploy that. Today, we're taking dfuseeos. So at the beginning, we had 15 or 16 Docker images, but now with Go, we were able to build one binary that has all the pieces of software that we just start separately. That's what we use. And to answer the question of EOS, Michael there about grouping things, it's a new world, even for us. We always have been running separate services because we didn't have the capacity before dfuseeos as a single binary to run multiple apps in one container or one process. But nowadays, I mean, we could slice and dice deployments in a very different shape. For example, all the injector, the fluxdb injector and the trxdb-loader, they both have the same role. They take data in, they flow it in their respective database. It makes sense to put them together, right? If one fails, it restart, and it's just gonna add a little time delay between, but every system is able to wait on that store being filled because they can stretch their buffer. You don't wanna do that for too long, but and then, you know, for a bunch of service like dgraphql, eosws, if you have a small network, you can put them together, expose the 2 ports, put them and serve them together. So it makes sense to have the types of service that are stateful, put them together, things that are stateless, and you think will scale together and put them, and you can put them together. Maybe the question you asked EOSIO Michael is about, you know, what could be reused between deployments. The thing is, I don't see, like, pretty much all the components there are very specific to the network it's addressing. I don't see a component that could live and be shared, except one is the etcd cluster. We actually use one etcd cluster and it's namespaced. So we have many networks to reuse the same etcd cluster. Again, tikv cluster, if you're to deploy that on bare metal, you can add a prefix to all the keys. That tikv is very, very fast to that because the way it's laid out in its tree there. So you can use one big cluster. We also do that with Bigtable. We use one big shared cluster. So these things can be operated separately for many networks. etcd can be shared, but the rest is very, you know, specific. So you have your own buckets or your own paths, at least for all the object stores that are used, 100 block files, indexes, so that also the indexes that go for search that are produced by the indexer. Does that make sense? Can DeepMind run alongside a state history plugin? Unrelated. So the DeepMind patch, if you enable it, will, where it passes, output things in lockstep with the reading process. It is not going to affect anything else. And I would assume, I think it's safe to assume that if you're running state history, it's not going to bother DeepMind at all. So you can safely run the two together. I haven't tried myself, but I see no reason why these things would conflict. So you let Elasticsearch, any plans to get it from some DDB instances? You know, these are sort of things we called edge integrations. It's our goal to have diffuse, you know, fire hose data in every location. We have specialized service that we think are make querying a blockchain extremely reliable because they're understanding of forks and give guarantees to users. But putting irreversible data in a million data stores is certainly something we want. And someone at Hackathon like started a Kafka outputter, right? And but based on that data and the sort of guarantees you have from the get-go, the fact that you can, after the fact, without replaying the chain, navigate and know that you're going through an irreversible segment and then keep that information and then write it to a certain database. These things are going to be 500 lines, 600 lines. The Kafka plugin we have is just one simple program, but it uses the data in there. It uses the fork DB. It puts a filter. I want only irreversible stuff, and takes the content, which is just, you know, a protobuf with the traces and the action, and then you decide what you want. You turn around, you write to whatever. And that can be done very easily. So is it in our plan? I mean, I would love to see contributions in that regard. I guess that's the answer. But right now, I'm not coding this tomorrow, but we've tried and we want to do it slowly. I don't have that in a roadmap direct, I guess, is my answer for that particular one.
Cool. Yeah, that was a lot of fun, I think, for everyone. We're running out of time, of course. It's almost 11.
I'm fine. I'm fine. If you guys want to leave, you can leave. If you want to stay, I can stay.
Let's give ourselves maybe 5 more minutes. Right now, we don't have any questions.
Okay.
Thank you to everyone. It was great to have you all during this first webinar. Like I said, like, we're going to work on the glare on the whiteboard. That was not intentional. We're learning as we're going, but that was a lot of fun. Thanks, Alex, for all these explanations.
Is there anything we need to be useful that I forgot?
I think it's important to remind everyone for any questions you may have that come up today, tomorrow, next week, next month, the best place to get your questions answered would be the issues section of the dfuseeos.io repo. That's where our engineers have their eyes on all the time, and we'd be very happy to help you there.
Right. Okay. There's a Q&A there that popped in. No? Getting a specific block height, of course, and that's a special database. I've never seen that. We've crafted it especially for that, and so we're working also. I can tell you that we're working on some tools to get from that block state and run through a migration to boot a new chain. You know, I've shown you eosc boot. No promise here, but I'd like to make that a unified process in dfuseeos so that, you know, we start a chain, but it also has a boot sequence and it comes with some of the pre-configured whatever, and people could craft boot sequences that include certain version of contract, certain setup. Like, you don't need to do that all by yourself, and also be able to turn around, query fluxdb on one side to get content put on disk, run some sort of migration script or whatever, and then you know, inject that in the next chain with the account set up the same way perhaps as the previous chain, with the data put in place at the same place it was, but maybe mutated with a new contract. So you can easily pass from one chain to the other, you know, with just a few commands. So it would dramatically, I think, improve the developer flow. If that's interesting to you guys, poke me. I'd like to get your feedback on that. Microsoft independently, wrapper that uses Microsoft an example. Each Microsoft you use independently, but have you a wrapper that use at the microservice as an example? They can all be separate independently. Maybe rephrase the question. I'm not sure I get the question. A wrapper, I guess I could go into network topology, but these things can all be in separate container, listen to their port, be connected together separately. There's no wrapper necessary. And the API proxy I showed is optional. If you want to have we use a Kubernetes ingress. So that's how things are routed to the different services. We're using the service topology of Kubernetes. So we don't use an API proxy. API proxies to facilitate the work on the local development machine. I don't know if that answers the question. Otherwise, post another one. When modifying system, no. So we've always, you know, dig deep in the, so the question was, do we need to modify system contracts for diffuse to work? No, there's no assumption of anything except the core tenets of the chain. And we've always made the top level diffuse stuff just manage whatever, you know, semantics that are native to the chain. So it doesn't preclude you from, you know, being specific onto what you build on top, have specific queries or extract specific fields. The only thing I think maybe that is specific to certain contracts is the search fields that are indexed today is a selection that we made, like the data.from, data.to is a selection we made as when we looked at the beginning of the chain, or after that we revised a few times, but what are the most popular fields and what are the most queried fields, and we decided to index these nowadays. So right now it is not yet possible to configure that, but it's my goal to have these things configurable from either the command line or a file where you say the fields you want to index, and when you index them, well, you get just these maybe, and we already have a way to filter in the search engine to filter what is being indexed by using the common expression language, common by Google, which is something that they use for their ACLs. So the common expression language here is you know, a very simple language like that, and you can give, it has all these, you know, funky functions, but in our case it just says, okay, if account equals let's say IDOS, then you put that in a black list or you have a white list, and using that language is very powerful. You can select what gets indexed, but what's missing is what then when you choose to index an action, which fields in that action get indexed. And that, I think I drifted a little bit from the question. I don't see the question anymore, so I'm not sure. Oh, it's in there. I should. So yeah, so we don't need to modify system contracts, but you might want to configure your diffuse instance for certain aspects. If your chain, you know, doesn't have IDOS, you don't need to filter it. Or if it's important on your chain to have IDOS, then you can take out the filter. Actually, IDOS is sort of blacklisted by default in the default config. Just be aware of that. Is that
Awesome. Yeah, I think we're going to wrap it there.
Okay.
Thanks, Alex, for your time. We have to keep him on track. Thanks, everyone. Again, it was a lot of fun to have you all.
Don't forget to go to the repo, dfuse-eosio. And if you haven't done that already, you can star the repo. So you'll see if we do send some release and whatever. And this is good karma if you like what we're doing. I don't know what karma is about, but I mean, that would be a great idea for all of you today. You can do it exactly right now while I'm talking. And I mean, that shows your love. That shows your appreciation for the time we took for you today. Is it done? And we can see you next time.
Yeah, it was a lot of fun. Thanks again, everyone. And we are recording this, so we'll be able to share it with you as well. Thanks. Have a good day.